Hello and welcome to this video about limits and continuity. This is the second video on the same subject on limits and continuity. The first video covered sections 1 through 4. This video will start from section 5, and you can skip the objectives because the objectives are the same but the contents are not. Objectives: interpret the rate of change at an instance in terms of average rates of change over intervals containing that instant. Represent limits analytically using correct notation. Interpret limits expressed in analytic notation. Show that for a function f, the limit of f of x as x approaches c is a real number r if f of x can be made arbitrarily close to r by taking x sufficiently close to c, but not equal to c. If the limit exists and is a real number, then show that the limit can be expressed in multiple ways, including graphically, numerically, and analytically. Section 2.5. Conditions for existence of a limit. We will show the limits of a function when x approaches a point in the function's domain from the left is not equal to the limit when approaching the same point from the right. In such case, we say the limit does not exist. That is, the limit will exist only when approaching a point from the left has the same limit as approaching the same point from the right. Also, we will consider when approaching a point that is not in its domain. The existence of the limit in this case depends on whether or not the limit when approaching the point from the left equals to the limit when approaching the point from the right. We're going to go ahead and take a look at a couple of different situations for limits, but before that we have a key on the lower left corner, and the key states that if we use D and E, then we mean that the limit does not exist, and if we use U and D, that means the limit is undefined at a certain point. Having stated so, then let's get going with our. We have the xy axis. I did not mark the point 3 and 5 on the y-axis because they are not going to be of interest for us. So this is the y-axis and this is our x-axis. Let's go ahead and consider this function. We have the first function to discuss, which is y equal to f of x. We can see that we obtain the limit as we approach from the left, and we obtain the limit as we approach from the right. The limit as we approach from the left is equal to 6, which is right here. The limit as we approach from the right, we can trace it, and it is equal to 8. So we have the limit equal to 8. The limit as we approach from the left is not equal to the limit as we approach from the right. What does that mean? That means the limit does not exist. Very important. When the limit approaching from the left is not equal to limit approaching from the right, the limit does not exist. Very important. Even though we know that the point 8, which is the point of focus, because we are taking x towards 8 from the left and taking x towards 8 from the right. So our focal point is x, is 8, x equal to 8. So the value of the function when x equal to 8 exists and equal to 7. And this is the value of the function. So just because the value of the function exists does not mean that the limit will exist. The existence of the limit does not depend on whether or not the point itself is on the graph, is on the domain of the function. It does not. Let's take a look at a second example. Second example, the only difference between this example for the function y equal to g of x, the function g of x, the limit as we approach from the left is equal to the limit as we approach from the right. So What is the advantage of this is that the limit exists when we approach x, unlike the first case that we talked about. So the difference between these is that over here the limit exists, and when it's approached from the left is the same as when we approach from the right, and for that reason the limit exists. Let's take a look at a third case. The third case is pretty much y equal to h of x. It is similar to the first case. The only difference between the third case and the first case is the fact that the point 8 is not on the domain of h of x. X is not in the domain of h of x. Since it's not in the domain of h of x, that means h of 8 is undefined. And the fact that if we look at the domain, if we look at the limit as x goes to -8 and the limit as x goes to +8, they are different. So this limit is different from this limit. They're not equal. Since they are not equal, we said the conclusion, the limit does not exist. Okay. Once again, the difference between this function and f is the fact that on f we have f of 8 defined. So f of 8 defined, but in y equal to h, f of 8 is not defined. So the fact that f of 8 is defined did not lead to the existence of the limit. That's the point. That's very important. F of 8 may exist, but the limit may not exist. Over here, neither the limit exists nor h of x is defined. Now we're going to go ahead and take a look at the definition. Let C be a real number that's either an interior point or an endpoint of an interval in the domain of f of x, function f. So the function f is continuous at C if we get the limit as x goes to C is equal to f of C. One more time. If the limit of f of x as x goes to C equal to f of C, then we say that the function f is continuous at C. Second, the function f is right continuous at C, or continuous from the right, if limit as x approaches C from the right of f of x equal to f of C. The third is the function f has left continuous or is left continuous at C, or continuous from the left if the limit of f of x as x approaches C from the left equal to f of C. So these are the three cases. Let's demonstrate these three cases with one of the examples that we just mentioned. If you look at this example, we see that g of x is a function. If we approach the number 8 from the left, the limit is 5. If we approach the number of 8 from the right, the limit is 5. Since the limit in both cases are equal, then we say the limit exists, which is right here. We talked about limits and continuities, but we did not talk about how we or whether or not we can tell if there is continuity. And for that, there is a test for continuity. Let's take a look at the test for continuity. The test for continuity is as follows. A function f of x is continuous at a particular value of x equal to C, for example, if and only if it meets the following three conditions. F of C exists, and the limit of f of x as x goes to C exists, and the limit of f of x as x goes to C equals to f of C. What does the first one mean? The first one means C lies in the domain of f. What does the second one means? The second one means that f has a limit when x goes to C. And the third one, identify the limit. What is the value of the limit? It says the limit equals to the value of the function evaluated at C. So let's take a look at an example for each of these. Here, this function we have already determined as x goes to C, the limit will be equal to 5. as x goes to c from the left, and as x goes to c from the right, the limit is also equals to 5. Since the limit as x goes to c from the left equal to the limit as x goes to c from the right, then this will lead us to the conclusion that we talked about, is that the limit as x goes to c exists. And one more thing, here we know that c is part of the domain. It's in the domain of y equal to g of x, and for that matter g of c is a value that exists. So since g of c equal to 5 and it exists, this satisfies number 1. Number 1, f of c exists. So this number 1 is satisfied. Number 2, it says limit as x goes to c of f of x exists. And we've just proved that the limit exists. So this is number 2. Number 2 is satisfied here. So number 2 is done with. And we said that number 2, f has a limit as x goes to c. And this, the justification for this limit to exist, limit of g of x to exist, is the fact that the limit going from the left to the point c is the same as limit going from the right. Now, the last point is limit as x goes to c of f of x must be equal to f of c. And we can see that limit as x goes to c of g of x equals to 5, but 5 equals to what? Equal to the value of the function evaluated at c, which is equal to 5. So number 3 is satisfied by this too. So number 3 is also satisfied. These are very important theorems. So let's just take care of them. Let's take a look at another case and compare it. If we look into this case and this case, we will find one thing that's different. Over here, the limit as we approach from the left is the same as limit as we approach from the right. Over here, that's not the case. The limit as we approach from the left is not equal to the limit as we approach from the right. They're not equal. If they're not equal, then the limit does not exist. So the limit does not exist. Although the value of the function evaluated exists. So number 1 is satisfied. Okay. Number 2 has a limit. No, number 2 is not satisfied. So number 2 is not satisfied over here. And number 3, the limit equals to f of c. If it doesn't have a limit, then we cannot say that the limit equal to f of c. So it's not satisfied in both of them. Let's cruise through these, and then we can see that we have an open interval from this end to this end, and we have the point where x is equal to 0, and we have a dot here. The dot is closed. Since the dot is closed, then the function is continuous at this point. This point is x equals 0 and y equal to 1. So it's continuous at this point. Over here we can see that we have a dot, but it's open, so there is no continuity. The function is not continuous. And on this one, the function is not continuous for the same reason. Over here, the function is not continuous because we have a jump. The function jumps at 0. It's at 0, the function jumps that way. And of course, it's not defined when we're coming to the left. We're not reaching 0. We're reaching 0 if we're coming from the right. But the fact that we have a jump, this is called a jump. The function jumps from 0 value here. From 0 value when x less than 0, f of x equal to 0 over here. So when x less than 0, f of x equal to 0. But also when x equal to 0 or more, that means greater than or equal to 0, the function has a value of 1. So the value of 1 over here and the value of 0 over here, it means that there is a jump. So we're jumping from y equal to 0, we're jumping straight to y equal to 1. So this jump makes the function not continuous. And if we look over here, we can see that there is asymptote. There is a vertical asymptote. That means this line will continue to infinity before it gets closer to the y-axis. And also its image will do the same thing. and that's why we don't have continuity. That means the function is not defined at 0. And over here we have sine equal to 1 over y equal to sine 1 over x. Also, this graph is not defined at 0. So that's why we have also at 0 discontinuity. Properties of continuous functions. If the function f and the function g are continuous at x equals c, then the following algebraic combinations are continuous at x equals c. The sum of the two functions, the difference between the two functions, multiplication of functions by a constant, multiplying two functions, dividing a function by another one. In this case, g of c shall not be equal to 0. Raising a function to the power n. N must be a positive integer. Taking the nth root of a function. This provided it is defined on an interval containing c and n is a positive integer. Now we're going to go ahead and take a look at composition of continuous functions. F is a continuous function, is continuous at the point C, that means C is in its domain. And G is a continuous function, and G has f of c in its domain, so G is continuous at f of c. And we see that f picks up c and pass it over in its range to f of c. But f of c is also the domain of G, so G takes f of c and maps it in its range, which is G of f of c. We have a function that will do both steps in one shot, and this function is G circle f, which is called composite function. G circle f will take c and move it all the way to the end, which is G of f of c. Now that we have talked about this, let's just discuss a few things. The first thing is that we have this as a dot, and this dot is closed. Since this dot is closed, then at this point C, the function is continuous. So the function is continuous at this point C, and C is in the domain of the function. To the other side, if we have an open dot, this dot is open, so that means the function is not continuous at C, and C is not in the domain of the function. Let's just keep this one in mind, and let's take a look at the mapping that we have over here. To start with, let's take a look at the key for the mapping. When we use D, we mean that it is for domain, and when we use R, that means it is for range. Now we have, here is the mapping that we have. We have the function f, and its domain contains C, so f takes C and produces f of c in its range. But the range of the function f is the domain of the function g. So g takes f of c and maps it into its range to g of f of c. So this particular range, this is the range of g, and at the same time this is the range of G circle f. Also, if we look at this, we can see that this is the domain of f, and it's also the domain of G circle f, because G circle f takes C and maps it all the way to its range, which will become G of f of c. So this is pretty much similar, identical to what we have over here. The mapping on this side and the functions on the other side, they are identical. So what we have, one more time to conclude, we can conclude that if C is a continuous point in the graph of f, and f of c is continuous point in the graph of g, then C will be a continuous point in the graph of G circle f. That's the conclusion that we're making here. So the conclusion is now a theorem. Theorem number 9, composition of continuous functions. If f is continuous at c and g is continuous at f of c, then the composition G circle F is continuous at C. If it's not clear, you could go back to the previous slide and it should be very clear by now. This is the second theorem on limits of functions. Theorem number 10. If limit of the function f of x as x goes to c is equal to b, and we have a function g that is continuous at the point b, then limit as x goes to c of g of f of x must be equal to g of b. Before we talk about it, let's go ahead and try to take a look at the following figure, which documents the relationship between the domains and the ranges. Here is a function f. Here is a domain of the function f represented by x, where x represents all the members of the domain of the function f, including c. And of course, f receives as input members with the domain, and it produces as output members in a range. So this is the range of the function f, contains f of x. And also we're going to include along with that what is given in the theorem, which is limit of the function f as x goes to c is equal to b. We're going to include it as one of the members of the range of the function f. But the range of the function f is the domain of the function g. So the function g takes as input elements of its domain, so which is this one, and is going to produce g of f of x in its range. So that is the first member in this range. The second member is in range is the b. It's going to take the b and is going to operate on it and produce g of b, and it's another member of its domain. So this is second member of its domain. Let's try to summarize what we just talked about. First of all, the first thing that we can summarize is the following. The domain of G, which is right here, this is the domain of G, has f of x and b as members. And here is f of x and here is b. Thus, the range of G will contain g of f of x and g of b. And we mentioned that the range here of G contains g of f of x and g of b. So what is the conclusion here? Therefore, the limit of g of f of x as x goes to c, this is the one, the limit of g of f of x as x goes to c equals to g and then the limit of f of x as x goes to c, and that's going to be equal to g of b, and that proves it. In such a case, the function g must be a constant function. Let's take a look at the following diagram. What we have in blue is the function f, and if we take x, this is the x-axis and this is the y-axis. If we take x approaching c from the right and x approaching c from the left, then the limit of the function f as x approaches c is going to be the value of the function at this point, which is b. So which is given over here. So this is what is given, we're proving it over here. This is the proof for this limit. So the limit as x approaches c from the right and from the left is equal to b. So this is the point c, it's equal to b. And then since f of x, which is all the members of this line, are input to g, and we know that g is a constant function, so g of anything is equal to b. So all these members will be fed into g as input, and all of them will result in one output because g is a constant function. All of them will result in one output, and that is b. And that will prove our theorem. The intermediate value theorem for continuous functions. if f is a continuous function on the closed interval ab, and if y0 is any value between f of a and f of b, then y0 equal to f of c for some c between the 2 points a and b. And if we look at this and assume that it's a process, then it is in between a and b, and this is the closed interval where b has a measurement of like f of b over there, and a has a measurement like f of a over here. Then we must have a y not between a and b for which there is a measurement between a and b, and we're calling that measurement c. Let's try to trace the speed of an automobile, for example. Let's suppose that the automobile started at speed equal to 0 and ended at speed equal to 6, for example, or 60. The speed is 60. And let's suppose that it did this one in 6 seconds. So let's pick over here. Then our f of b will be equal to 60. Our f of a will be equal to 0. That's the speed. And of course, this speed, it took 6 seconds. So from second 0 to 6, it took 6 seconds to reach that speed. So if we can ask ourselves this question, what about the time if the speed over here was 30? The speed is half. So if the speed is 30, then there must be a point between 0 and 6 for which the speed is 30, and that point is the 3rd second. So at the 3rd second, the speed will be 30. Because the speed is pretty much every second, it increases speed by 10. So the rate of speed is 10 per second. And that's why if we pick the speed 30, that means at the 30th speed, the second is 3. At the 60th speed, the second is 6. At the 0 speed, the second is 0. And that's exactly what the intermediate value theorem is about. Now for this particular figure, we have the function defined as follows. F of x is equal to 2x minus 2 when x is greater or equal to 1 and less than 2. And it's equal to 3 when x is between 4 and 2, including 4 and 2. And then here is a statement. The function does not take on values between f of 1, which is 0, and f of 4, which is 3. That means a value between this and f of 4. It does not take, it says it does not take values. That means it misses which values? The values between 2 and 3. The values between 2 and 3 are these. So we cannot find, or if we picked up a value, for example here 2.5, and we want to ask what is the value on the x-axis, we cannot. So the intermediate value theorem, when we have something like this, then we will have a matching point in between the closed interval, which is in this case the closed intervals a and b. So we can see that there is a vacuum here. We can pick values between 2 and 3, but we will not find a value that's matching them on the x-axis. So this shows that the intermediate value theorem does not apply in this particular case. We will continue about continuity. Let's take a look at the two graphs that we have. We have one graph for lowercase f of x, and we have another graph for uppercase f of x. The difference between these two graphs is as follows. For every x such that x is greater than or equal to negative pi over 2 and less than or equal to positive pi over 2, f of x, capital F of x is equal to lowercase f of x, except, we have exception, except for x equal to 0. They're not equal. Why? Because this function have an open dot here, and this function have a closed dot. What does it mean to say open dot? That means the point 0, 1 is not in the domain, is not in the domain of f of x, is not in the domain of f of x. So that's why there is discontinuity here. To fix this problem, we can get the limit. Let's try to get the limit of this point as we approach from the left and from the right. If we did the limit, we're going to come up with something like this. Limit f of x as x goes to 0 equals to 1. Now we have a value at this point. So if we assigned the function f of x, if we assign, for example, f of 0 to be equal to limit f of x at x goes to 0, then we will have solved the problem. Because in that case, we know that the limit is equal to what? The limit is equal to 1. So f of 0 is equal to 1. Since f of 0 is equal to 1, that means here we don't have the open dot, we have a closed dot. And that fixes the problem of discontinuity at the point 0, 1. We don't have it here. So capital F of x is the saver for us. Like we said, for every x in the domain of both functions, f of x, capital F of x equal to lowercase f of x, except for when x is equal to 0. Because over here we patch the 0. So f of 0, capital F of 0 is equal to 1. Over here, lowercase f of 0 is not equal to 1. It's undefined. We will continue discussing this one on further lessons.